Welcome to the Planetary Sample Science Seminar Series, or as we like to call it. We are really excited today to have Dr. Steve Elardo. So Dr. Steve Elardo is an assistant professor in the Department of Geological Sciences at the University of Florida. After earning a Bachelor of Science in Geosciences at Stony Brook University in 2008, he earned his PhD working with UNM's Chip Shear at the Institute of Meteoritics in 2014, where his work focused on both the early magmatic evolution of the moon, as well as the origin of some of its, at the time, youngest known magmas. He then moved to the Carnegie Institution for Sciences in Washington, D.C. as a postdoctoral researcher, where he continued studying the moon, while also branching out into using non-traditional stable isotopes as tracers of planetary magmatic processes. He then joined the faculty at the University of Florida in 2018 and established the Florida Planets Lab group there. And Steve, if you are ready, please go ahead, take it away. We are super excited to hear from you today.
Sure thing. Thanks so much. Can you all hear me okay?
Yep, we hear you perfectly.
Wonderful, wonderful. Thanks so much. Well, great to be, I guess, virtually back at UNM and virtually back in room 340 in Northrop, which I don't think that I've been in since I defended my PhD, 10 years ago now. Don't know how that happened. Anyway, so I want to tell you all a little bit about some of the work I've been doing here the past year or two at UF in my experimental petrology lab, dealing with investigating the mantle sources and really the ultimate origins of the magma that was collected by the Chinese Chang'e 5 mission to the moon a number of years ago. So, like so many questions in lunar science, what we know about the moon and the ultimate answer to this question that I'm going to be addressing today ultimately comes down to the fact that the moon is highly asymmetric. Its near side and its far side have a number of different asymmetries, and these asymmetries are arguably the moon's most defining features. So what do I mean by these asymmetries? And some of you may already know this, but let me go through them. So first of all, the moon's crustal thickness is highly asymmetric in an Earth-referenced direction. The far side crust of the moon is about twice as thick as the average crust on the near side of the moon, and you can see that in this altimetry map from Lunar Reconnaissance Orbiter here. The asymmetries don't stop here. If we look at the surface expression of magmatism, the volcanic outcrops on the moon, about 97% of the surface area of lava flows occur on the near side of the moon, only about 3% on the far side. And then if we look at the geochemistry of the lunar surface, we also see that it is asymmetric. We have these highly thorium-enriched areas on the near side. This is a terrain that is called the prosolarium creep terrain. We see very high abundances of thorium and other elements as well that aren't really expressed on the lunar far side. So a lot of my talk today will be dealing somewhat indirectly with these thorium-rich areas and what exactly they are and their influence on lunar evolution. So what you're looking at when you look at that kind of thorium map and see those enrichments in thorium and corresponding enrichments in things like potassium and uranium and the rare earth elements that you can't see in that map, you are seeing the surface expression of a reservoir that lunar scientists call creep. Now, what is that? So creep is the term that we give to the last liquid that formed in the lunar magma ocean. So if we look at this sort of time sequence for the lunar magma ocean, we start with a moon that is probably completely molten right after the giant impact. And much like a planet-sized layered mafic intrusion, it starts crystallizing mafic minerals first. Olivine and pyroxene, those pile up to form the mantle. We have a plagioclase crust that floats at the surface to form the lunar highlands crust. I know this is all review for most of you, but I really want to emphasize that last little residual liquid there, sort of sandwiched between the crust and the mantle, we think, that's the creep reservoir. And that's what we see expressed on the surface in the prosolarium creep terrain. Why it's only expressed on the near side of the moon, not the far side, still an open question. But that's sort of what we think that surface expression is that the creep reservoir, and it's very much enriched in things like rare earth elements, large ion lithophile elements, high field strength elements, and very importantly, radioactive elements, potassium, thorium, and uranium. These are very incompatible elements, and so they naturally concentrate in the liquid. And creep is going to have because it's enriched in things like the rare earth elements, it's going to have very radiogenic strontium, neodymium, and hafnium isotopic compositions as well. So that, again, that thorium map is showing you the surface distribution of that last residual liquid from the magma ocean. Now, I want to jump here to a timeline of lunar magmatism before I keep going over the rest of the talk, just so we can kind of get on the same page with what are the ages for lunar magmatic events? How old are basaltic terrains on the moon? And sort of what are the timelines we're dealing with when I say a young lunar magma? What do I mean? So this timeline here just shows age in billions of years for different lunar magmatic events. And so we have start of the solar system up here, origin of the Earth and Moon. And then down here in these sort of green colors, we start getting into the ages for reservoirs on the moon itself. So the Mare basalt source, that is obviously the lunar mantle, the Farron and Orthosite suite, again, those flotation cumulates from the magma ocean. We have ages for creep itself. And then we have the ages for different post-magma ocean magmatic events. So the ages for the Highlands Magnesian suite that Chip and I have worked so extensively on in our respective careers. The Alkali suite, another set of intrusive crustal rocks on the moon. Creep basalts, and then this very long line here in pink for Mare volcanism. Mare volcanism being the main sort of pulse or pulses of basaltic magmatism on the moon. Now, up to the point of Chang'e 5, the youngest Mare basalts that we had, or the youngest igneous rocks, I should say, that we had from the moon, were just slightly younger than 3 billion years old, which is where this solid portion of this line stops right here. So for a terrestrial scientist, you may look at that and say the youngest igneous rock you have is 3 billion years old. Well, moon is smaller, higher surface area to volume ratio. It cools more quickly. So we should expect that the moon probably has igneous rocks that are significantly older than a larger planet. Now, the Chang'e 5 samples extended this range out to 2 billion years, which is the radiogenic isotope age determined on the basalt's return from Chang'e 5. Now, there's circumstantial evidence for volcanism younger than that. We have things like irregular mare patches, which have been dated through crater counting methods to possibly as young as about 18 million years old. And then we have the Nature paper from a few weeks ago suggesting a few pyroclastic glass beads from the Chang'e 5 mission that are on the order of 120 million years old. I think that there's a significant, my opinion is that there is a significant amount of skepticism in the community for both the ages of the irregular mare patches and those glass beads. That might be a little controversial, but I think that those, the veracity of those ages is going to require some additional verification. So I'd say the youngest widely agreed upon igneous rock age for the moon is about 2 billion years old. And that again is the Chang'e 5 samples that I'll be talking about today. Okay, so back to creep for a moment, because it is, again, one of the main hosts of heat-producing elements in the moon. We say it's this, the last liquid from the magma ocean, but what actually is it? And unfortunately, we don't really have a hand sample of creep. What it is it's a component, a chemical component that we see in some lunar rocks, and it has relatively uniform trace element ratios and radiogenic isotope compositions, but we don't actually have a hand sample of it. What we do have is samples that seem to be enriched in creep, and a lot of those that are collected on the near side of the moon are not basalts, they're not igneous rocks, they're impact melt breccias. And they're impact melt breccias like the breccia 14310, which we think is likely a piece of ejecta from the Imbrium basin. And so we're not seeing a ton of magma mantle-derived melts after the early crust building stages on the moon that contain creep. What we're seeing spread across the surface is very much linked by many folks to Imbrium ejecta. So most Mare basalts, despite being found in the Procellarum creep terrain, and you can kind of sort of qualitatively see the correlation between the enrichments in thorium on these maps and the surface expressions of basalts. Despite that general correlation, most Mare basalts are not creep rich. So that's just kind of an interesting point, and it's one of the things that we still don't fully understand about the moon. And there's a lot of things we still don't understand about why creep is only dominantly found on the near side of the moon. Where exactly is it? We see the surface expression of it in remote sensing data, but is there more beneath the crust still? Has it been convected into the deep mantle? Did it stay below the crust? Is it still there now? Where was it throughout most of lunar evolution when the moon was generating Mare basalts? And why the connection? We see sort of the physical spatial connection on the surface between the Procellarum creep terrain and Mare volcanism, but why aren't most Mare basalts creepy? Why aren't they creep rich? So that's some of the questions that I think still drive the community and that I'm going to attempt to address today with the Chang'e 5 samples. So some of the things that have sort of driven my research the past few years are investigating how the moon's creep reservoir is connected to Mare magmatism. What are those connections? Are they direct? Are they indirect? And then how did creep affect prolonged lunar magmatism? So we have this enrichment of these elements that are producing lots of heat throughout lunar history. How is this connected to the moon's ability to make mantle-derived melts through time? And what do the youngest lunar samples say about this? So when I was at UNM working with Chip during my PhD, we investigated a suite of lunar meteorites that, again, were at the time the youngest samples derived from the moon. But now Chang'e 5 has changed that, and we have these younger samples. So at this point, let's switch gears a little bit and talk a little bit about the Chang'e 5 mission. So this was the China National Space Agency's first sample return mission. They had run a few other landed Chang'e missions to the moon in the years prior to 2020, but Chang'e 5, which landed in northern Oceanus Procellarum, as you can see up here with this red dot. This was the first lunar sample return mission by any nation since 1976. And they specifically targeted a region of northern Oceanus Procellarum that crater counting had suggested was a younger basaltic terrain that had been sampled by any of the Apollo missions, the landing sites of which you see here in the yellow dots. Now, this uncrewed mission returned about 1.73 kilograms of rocks and regolith, and it got back to Earth in December 2020, and about a year or so later, maybe a little bit less than that, some of the first papers from the preliminary examination and science teams started to come out about the Chang'e 5 samples. So I just wanted to show you the image here of the landing site. So here on the right is this sort of fisheye lens view of one of the legs of the Chang'e 5 rover, and you can see one of the sampling instrument arms coming down here. I'm pretty sure that off in the distance, the hills you see here are the Mons Rumker volcanic complex, but I could be wrong about that. It's very close to the Mons Rumker volcanic complex, which you see over here in this image. But what we're talking about is sort of the western limb of the moon. So this here, you can follow my cursor, is the Imbrium Basin. And the Chang'e mission landed to the west of that, again, in northern Oceanus Procellarum. And so it turned out after dating of the samples when they were brought back to Earth that this is a 2 billion year old basaltic terrain. Now the region is also very much adjacent to what has been mapped as Imbrium ejecta that is very thorium rich. And you can see that up here on the top right map where we have this general low thorium spot here in the middle. That's the middle of the Imbrium Basin itself, and surrounding it, including right next to the Chang'e 5 landing site, is this really thorium enriched terrain that is mapped again as Imbrium ejecta. So not necessarily thorium rich igneous rocks, but rocks ultimately derived from excavation from the Imbrium Basin. Now, although the Chang'e 5 basalt that was sampled is about 2 billion years old, magmatism around northern Oceanus Procellarum and around the Mons Rumker volcanic complex spans at least 2 billion years. So other crater counting estimates for different lava flows in this region go back to about 3.9 billion years old. And remote sensing suggests that they're not all of the same composition. Over that 2 billion years or so, you have a diverse compositional range of magmas that have erupted in this region. So this is really indicative that in this region of northern Oceanus Procellarum, you had long-lived, perhaps sporadic, but long-lived production of mantle-derived melts from heterogeneous sources in the lunar mantle. So let's take a look now at the Chang'e 5 basalts themselves and some of their compositional characteristics. So here is a backscattered electron image of one fragment of the Chang'e 5 basalt, one of the samples from the Tian et al. 2021 Nature paper, which a lot of my work draws upon the data that they reported. So this texture, it's sort of a subophytic texture, and it is very similar to many other Mare basalts. You see small amounts of olivine. The basalt's dominated by highly zoned pyroxene and plagioclase. Overall, the basalt is relatively evolved on the spectrum of basaltic compositions. It has a low Mg number of about 32 and a moderate, on the lunar scale, moderate amounts of titanium, about 6 weight percent. It falls kind of nicely between the lunar groups of high titanium and low titanium Mare basalts. Now, to go with that low Mg number, it also has relatively high abundances of thorium, about 4.5 ppm thorium in the bulk rock. This is not as high as a creep basalt, but much higher than many other Mare basalts. And the rare earth element pattern of the rock is enriched in both REE abundances and specifically enriched in light rare earth elements. And I'll show you those data here in a moment. But on this plot here, again, from Tian et al. 2021 of bulk rock titanium versus the magnesium number, which is the molar ratio of magnesium to magnesium plus iron, we see in the sort of grayed out empty symbols here, data from Mare basalts from the Apollo and the Luna missions. And you have a couple of groupings here that predominantly don't overlap. So we have low titanium Mare basalts down here. We have a nice grouping of high titanium Mare basalts. And then the teal and red colored symbols are the compositions of various fragments of basalt from the Chang'e 5 mission. And this red hexagon is the average whole rock composition. Now, there's a lot of scatter in the Chang'e 5 data, and that's probably not due to scatter in the actual composition of the basalt itself, but more so probably scatter due to the fragments of basalt that were analyzed being very small and not representative of the whole rock composition. And so that's probably artificial scatter rather than real natural scatter. And that's sort of borne out by analyses of mineral compositions throughout the fragments that are all fairly consistent. But that sort of average composition has an Mg number of about 32 to 34 and somewhere around 6 weight percent titanium. Now, I mentioned the rare earth elements. So here we have a chondrite normalized rare earth element diagram. Many of you have probably seen this ad nauseum throughout your careers. And again, we have different rare earth element patterns for different lunar basalt suites in gray. And they're labeled, Apollo 12 olivine, Apollo 15 pigeonite, et cetera here. And now up here in green, we have a creep basalt. That is a creep basalt from Apollo 15. It's one of the sort of the type creep basalts that's referenced a lot in the literature. And then in the red dots here, we have the data from Chang'e 5. Now, initially, you might look at this and say, oh, well, this is a rare earth element enriched basalt that goes with thorium being enriched. And the pattern looks an awful lot like creep. There is probably creep in the origin of this basalt somewhere, either in the mantle source or it's assimilated creep on the way to the surface. This looks too much like creep to not be creep. Well, it's not creep. So here what I'm showing you is the far more definitive neodymium isotopic compositions for different lunar basalt suites. So what we have here, this is a TI diagram, time on the X versus initial neodymium isotopic composition in the epsilon notation here on the Y. So a chondritic composition or a bulk moon would be this flat line here at 0. And down here on this orange line, this is the creep evolution line. So any source region with creep in it has a certain samarium neodymium isotopic composition. And basalts derived from such a source will evolve along this line through time. We see that Apollo 15 creep basalt here. We see NWA 773, a creep-rich lunar meteorite here, and Apollo 17 creep basalt here, all nicely on this line. Now up here, we have the Chang'e 5 basalts. So they do not fall anywhere near the creep line. They have a source region samarium neodymium isotopic composition indicative of long-term depletion in incompatible elements in the source. So this on its own is, again, far more definitive than the rare earth element data and effectively rules out any substantial amount of creep being involved in the origin of this basalt. So that naturally leads to some more questions, especially when we're talking about the youngest lunar samples. So for these, the Chang'e 5 basalts itself, where in the mantle did these melts come from? Is this indicative of melting moving deeper with time? Just because as the moon cools, it's going to cool from the top down, basically, and so the deep mantle stays warm? Is this sourced from deep in the mantle? And then what is the heat source for prolonged lunar magmatism? If creep was definitively not involved in, at least directly, in the petrogenesis of these basalts, how do we keep the moon making magmas up through at least 2 billion years ago? So that's some of the questions that are driving this particular study. So let's tackle the first one. First question first. Where in the mantle did these melts come from? Did melting move deeper with time? And so the tactic that I took for investigating the depth of origin of the Chang'e 5 basalts is to investigate its multiple saturation point. Now, let me walk you through what a multiple saturation point is and how these investigations work. So any mantle-derived melt from pretty much any planetary body is going to have a pressure temperature phase diagram that looks something like the one I'm showing you here. So we have temperature on the Y, pressure on the X. And if you map out in PT space what phases exist at certain pressures and temperatures, you'll get a diagram that looks something like this. You'll have just melt at really high temperatures. Obviously, the liquidus is the point that the first mineral crystallizes. At low pressure, that's usually olivine. At a bit higher pressure, that's usually pyroxene. And at some point, you will have a crossover where you have on the liquidus both olivine and pyroxene existing together. And so with a couple of very important caveats, those caveats being, if a basaltic melt extracted from the mantle hasn't changed in composition significantly since it was extracted from the mantle, so hasn't undergone extensive amounts of fractional crystallization or assimilation, and it left behind two minerals in the mantle when that melt was extracted, in that case, the multiple saturation point in PT space represents the conditions of melting. Now, those caveats are important, and I'm going to address them for the Chang'e 5 basalts a little bit later, but let's keep this just in mind for now, that, again, if it hasn't changed in composition since it left the source, and it left two minerals behind, which we think is almost always the case for planetary mantle-derived magmas, the multiple saturation point is the conditions of melting. So for these experiments, though, it is crucial that one chooses a magmatic liquid composition. Now, you might remember from that titanium versus Mg number diagram I showed you earlier how much scatter there was in the compositions of the various fragments of basalt from Chang'e 5. That is really bad for this kind of study. So we need to make sure that we go through some filtering criteria in order to figure out what was the composition of the Chang'e 5 magma, the liquid itself. And to do that, what we did is we used models for the iron magnesium exchange for both olivine and clinopyroxene, calculated using published calibrations to first figure out what would be the magnesium number of liquids in equilibrium with the most magnesium olivine and the most magnesium pyroxene reported in any study so far from Chang'e 5. And that turns out to be a liquid with an Mg number of about 32. And so what we did here was we selected, using those criteria, the Chang'e 5 sample 103-001,005. You'll see that number a lot. This is the picture of it here. What's important is that the composition of that fragment itself has an Mg number of about 32. That is, again, in equilibrium with the most magnesium, olivine, and pyroxenes. And it has a bulk composition, the clast itself, that is very similar to the average composition of the Chang'e 5 basalt. So from that, I think we confidently determined that that sample is probably the closest composition we have to a true magmatic liquid composition for the Chang'e 5 basalts. And so that's the composition that we selected to use for these experiments. Now, our experimental approach was to determine the pressure temperature phase diagram for the Chang'e 5 liquid and to investigate any multiple saturation points on its liquid to interpret the origin of the magma itself. So we created a synthetic oxide mix based on the composition of that particular sample, which was, again, the liquid composition. Made this synthetic oxide mix. We dried it out and FO2 conditioned it at 800 degrees C. So we're starting with something that's as dry as we can get it. Did this in my Deltec furnace at University of Florida. And then that mix served as the starting composition for both ambient pressure gas mixing experiments and high pressure piston cylinder experiments at UF. And here is one of the 2 piston cylinders in my lab. For note, this is Freddie, and my other piston cylinder is Bowie, if anyone wants to make that connection. So this served as a starting composition for the experiments. We also ran phase diagram calculations using the thermodynamic modeling program Perplex. And I'll show you the results of those calculations after I show you the experimental data. So we essentially conducted experiments both at 1 atmosphere, so ambient pressure and variable temperature, to get the 1 bar crystallization sequence for this liquid. And then we took these the same mix to high pressure and temperature conditions in order to construct the PT phase diagram. Here's a backscattered electron image of one of the prettier examples of a run product. And so we have the graphite capsule here. We have this light phase here. This is just simply the quenched melt or the glass from the experiment. And we have a nice big euhedral plagioclase and a nice big euhedral pyroxene. Perfect. So different sets of experiments at different pressures and temperatures will reveal the changing liquidus mineralogy. From there, we can start drawing some phase boundaries and get into finding the conditions of multiple saturation, which is exactly what we did here. So this here is again a temperature versus pressure phase diagram for the Chang'e 5 basalt. Now, before we look at the high pressure results, I want to walk you through the 1 bar crystallization sequence, which I've highlighted here. So at 1 bar, the first phases to crystallize are plagioclase, followed very quickly down temperature by an iron titanium oxide, which is initially uval spinel and becomes ilmenite very quickly down temperature. So importantly, what we don't find on the liquidus here is olivine or pyroxene, mafic silicates. They don't appear within about 35 degrees of the 1 bar liquidus. Now, it's been used by the sort of rare earth element data, the enrichment and incompatible elements in these basalts have been argued by, I would say, most researchers in looking at the Chang'e 5 samples to be the product of extensive fractional crystallization of this basalt, which would make the kinds of experiments I'm doing here somewhat pointless. But the phases that most of those models use to fractionate are olivine and pyroxene. So if we don't have olivine and pyroxene on the liquidus at 1 bar, and fractional crystallization would probably be occurring at very low pressures, say in a crustal magma chamber before this gets to the surface, If that was happening, you would find olivine and pyroxene on the liquidus, and we simply don't. So if we move to high pressure now, I'm highlighting now the region where I'm inferring this liquid to be multiply saturated on the liquidus. And this occurs between about 0.4 and 0.7 GPa. And this liquid is actually saturated at this point with 4 phases, not just 2. Plagioclase, pyroxene, olivine, and at iron titanium oxide. And so we have the intersection here of these 4 phases in between this pressure range, and this pressure range corresponds to about 75 to 130 kilometers depth in the mantle. And if so these are all the experiments here. Let me just show you the results of the perplex calculations. The x-axis is going to change a little bit, so keep that in mind. But overall, the results are very similar. We have plagioclase at the 1 bar liquidus, and around 0.5, 0.6 GPa, we have a really complex multi-phase saturation point involving plagioclase, ilmenite, olivine, and pyroxene. So the perplex results seem to be corroborating our experimental results. And so I'm going to argue that that 4-phase multiple saturation point on the liquidus of the Chang'e 5 basalt represents the pressures and temperatures of melting for this magma. So the lines of evidence that I think support that are the convergence of not just 2, but 4 minerals at the MSP. And I'll point out, this is, to my knowledge, the first multiple saturation point for a lunar basalt that actually has a high titanium oxide on the liquidus. Despite higher abundances of TiO2 and other melts, they don't have it on FeTi oxide on the liquidus, but we actually do here. But we have essentially 4 phases converging in this narrow PT range. We have a lack of mafic silicates within 35 degrees of the 1 bar liquidus, pointing that would suggest that the basalt has not undergone fractionation of olivine and pyroxene in the low pressure environment. We have no reported olivine cores throughout any paper that I've seen for reporting Chang'e 5 sample data that would indicate a parental melt with an Mg number greater than 34. So that, again, would suggest that this basalt was not fractionating olivine and pyroxene necessarily before it erupted. We also have strontium neodymium isotopic compositions suggestive of plagioclase in the source region. So this plot here is the calculated source region RBSR and samarium neodymium values for model lunar mantle compositions. Now up here we have the measured compositions for creep, and off to the right on this diagram we have a lunar mantle end member, depleted end member that is calculated using magma ocean composition models. And the 2 curves here represent the mixing between creep and the lunar mantle in the solid line with plagioclase free cumulates, and in the dashed line with plagioclase bearing cumulates. And the Chang'e 5 basalt here, again, the hexagon, falls directly on the mixing line with plagioclase bearing cumulates. Now, again, our multiple saturation point was 0.4 to 0.7 GPa, and plagioclase should only be stable in the lunar mantle up to about 1 GPa. So if this result here is suggestive that plagioclase was present even in small amounts in the source region, that source region has to be relatively shallow. And then lastly, CPX thermobarometry conducted by Penny Weiser and her colleagues using data from the Luo et al. 2023 paper found clinopyroxene crystallization pressures from 0.7 GPa through to the surface, which is perfectly consistent with derivation from a source region at our multiple saturation point in terms of pressure, and then crystallization of those clinopyroxene phenocrysts from the source to the surface. So based on those data, I'm going to argue that our multiple saturation point does represent the pressure and temperature conditions of melting, and that this basalt has not undergone extensive fractionation after it was extracted from its source. And that first point says essentially what I just said. So what about the rare earth element pattern though? Right? Very, very enriched. It looks creepy. That to me would indicate a very low degree of partial melting. And because again, the strontium neodymium isotopic compositions point to very low degrees of partial melting, that basically can't have exhausted any of the foreign minerals in the source. And one of those seems to be plagioclase, again, from those isotopic compositions. So we see no evidence from the Chang'e 5 basalt that melting in the moon moved deeper with time. Again, this is an n equals 1 for 2 billion years ago, but it's right now the only samples we have, but they're the youngest samples, and they seem to be coming from a very shallow source region. And this is also suggested by the compositions of high titanium basalts. So when we think of deep mantle melting on the moon, oftentimes that's very much tied to the creep reservoir. There has been suggestions in the literature that there's a partial melt region surrounding the lunar core where the moon may still be molten to the present day, very deep down. That layer is oftentimes linked with high titanium cumulates, which are widely accepted to sink through convection after the magma ocean due to the differences in density and temperature. And very oftentimes in those models, high titanium cumulates are physically connected with creep. And so if those bring creep down into the deep mantle, where it can produce heat in the deep mantle, we should be seeing high titanium basalts that also have creep in them. However, again, if we go back to the neodymium isotopic compositions, high titanium basalts are almost uniformly depleted in their neodymium isotopes, and their rare earth element patterns are depleted in light rare earth elements. So they don't show the evidence of creep in their source regions. So I would say overall, between the suite of high TI basalts we have and now the Chang'e 5 basalt, there is in my mind, little to no evidence that creep was substantially carried into the deep mantle by cumulate overturn. And so that leads us into the questions of, if the Chang'e 5 basalts are derived from the shallow source region at 75 to 130-ish kilometers, how does the lunar upper mantle melt so late in lunar history? Why isn't this region cold elastic lithosphere at 2 billion years ago? So that's got the kind of questions that we're going to address here in the second portion. So to sort of frame the discussion and some of the calculations that we've done, I'm going to go back to the model of Lanouville et al. 2013. And they ran a series of global 3D convection models for the moon, where they placed creep dominantly on the near side of the moon. So accounting for the asymmetries in the distribution of creep that we see on the surface. And what they showed very quantitatively is that mantle temperature and melting is highly sensitive to where creep sits in the crust of the procellular creep terrain. So this is what I'm showing you here is a time series for one of Matthew Lanouville's models where creep is placed on the surface of the PKT. And we start at 4 billion years and go through to the present day. And what I want you to pay attention to are these white regions in here. So in his model, and he's using model compositions for the mantle, but those white regions are regions where melting is occurring in the mantle. It can be partial melting, but melting is occurring there. Now this model shows here, again, where creep is placed on the surface of the moon. And I'm going to flip now and show you the model where creep is all placed below the crust. And you can see how that region of partial melting grows in both space and time. So I'll flip just back and forth between these two. So again, surface layer, subcrustal, and flip back and forth just to really emphasize that the location of creep in the crustal or upper mantle column really does make a difference for how much melt the mantle is producing. And this is a function of the really low thermal conductivity of a northocite, which is dominant in the crust compared to a higher thermal conductivity in the mantle. So what we wanted to do for this study is examine the regional effects. So Matthew's models are great for thinking about how the whole moon behaves, but how about a particular region? And so again, we'll go back into the region of Northern Oceanus Procellarum, where we have the Chang'e 5 landing site here highlighted in this red dot. And we have, again, 2 billion years of magmatism in and around Mons Rumker. And we wanted to construct a simple local thermal model to test the idea of there being a subcrustal creep layer in this particular region. And so across this orange line in this image, with my collaborator, Matt Sigler, we set up a simple COMSOL multiphysics model to put together a thermal model for what the crust and the mantle may look like in this particular cross section here. And I just have an extremely schematic model here showing what it might look like. Again, we have this creep-rich Imbrium magenta here to the east of the site, and that's really highlighted by the thorium hotspot at Myron Crater. We have some anorthosite crust. Grail data suggests it's maybe about 30 kilometers thick here. We have the mantle, and then a variable in our model will be the presence or absence of this creep layer here. Now, when I show you the results, I want to emphasize this is not meant to quantify the actual temperature of the mantle at 2 billion years ago. For that, we would need to take into account mantle convection and other factors that can move around mass and heat. What we're really interested in is the relative difference in mantle temperature from the presence or absence of creep layers below the crust of different thicknesses. So the temperatures aren't going to make a lot of sense. What is really important is the difference in temperatures between models. That's really what we're after here. And so for these models, what we did is we used the composition, the abundances basically of thorium, uranium, and potassium from the Chang'e 5 samples. We used trace element partitioning parameterizations from the literature and assumed a low 5% degree of partial melting to calculate how much potassium, thorium, and uranium would be in the mantle source. The abundances of those elements in high K creep came from Paul Warren's classic compilation of creep-rich samples. And we used lunar prospector data for this creep-rich terrain here and the compositions of crustal anorthosites from the Apollo collection to calculate how much of those elements would be in the crust. Now, from the Lanouville et al., the global studies, we've taken some of their parameters, such as an initial adiabatic mantle temperature profile post-magma ocean. We've used the same thermal conductivities and heat capacities from their model as well. Now, these models were run for 4.4 billion years, and the results I'll show are a time slice at 2 billion years. So that's really what's of most interest to us. Okay, so here's now the schematic with the results for the base model where we have no subcrustal creep layer. So what you're looking at here is just simply distance versus distance. These are 150-ish kilometer distances for the depth and superficial distance for these models. We have, again, this 30-kilometer thick crust, this heat-producing creep-rich Imbrium ejecta layer here, but in this model, we have no subcrustal creep layer. And then here are some of the parameters that we've used in the model that I mentioned earlier. Now, here are the results here on the right. So again, we have depth versus distance. You can see near to the surface a slight effect in subsurface temperature from this creep-rich ejecta. But essentially, most of the heat from the Imbrium ejecta is radiated to space and not transferred into the deep mantle because of the low thermal conductivity from the crust. Now, this is no great surprise. Matthew's global model showed this really effectively. And down here, I'll just point out the temperatures of about 300 degrees C at the deepest extent of the Chang'e 5 source. Again, heat from mantle convection is not included here, so this number is relatively meaningless. What's going to be more meaningful is the number I show you on the next slide. But just to summarize here, basically the creep-rich ejecta from Imbrium anywhere on the surface of the moon provides a negligible amount of heat to the mantle. So that's not really moving the needle very much, and that's very much consistent with the Lanouville et al. Global models. And also, too, the amounts of thorium, uranium, and potassium in the Chang'e 5 mantle source, although high compared to most other Mare basalt sources, really aren't sufficient to generate melt at 2 billion years ago. So next slide, I'm going to show you the results where we add a 10-kilometer thick creep layer into the static model. Again, I'm going to emphasize the temperatures are not important. What is important is the difference. And with this 10-kilometer creep layer here, we have an increase in temperature at the Chang'e 5 depth of about 500 degrees Celsius from having this here. So with that subcrustal creep layer and thorium contents in that layer of about 22 ppm, which is consistent with the Warren calculation, the upper mantle of the moon in this region should be about 500 degrees hotter at 2 billion years ago than it would in the absence of that layer. So this really emphasizes that the location of creep is very much important in the crustal column, and you have 500 additional degrees of heat that you can play with to prolong magmatism in this region. So we see conductive heating of the mantle as an important source of heat, in addition to mantle convection, for prolonging lunar magmatism. And so this is a block diagram here, just kind of showing what I'm envisioning for the crust and upper mantle in the area of northern Oceanus Procellarum. We're looking at this from the northwest. And so we have Myron Crater here. We have the Chang'e 5 landing site here. I'll point out the silicic Myron domes are also in this image. And so what we have is this thorium-rich ejecta layer from the Imbrium Basin. Myron Crater exposes that thorium-rich material really well. We have an anorthosite-dominated crust of some thickness. Again, Grail suggests it's about 30 kilometers in this region. And we're invoking a widespread, perhaps discontinuous, but substantial subcrustal creep layer. So maybe on the order of around 10 kilometers thick. But again, that's very much, that's unconstrained at this point. What we need is about that much to generate, say, 500 degrees of additional heat. If you make it bigger, you'll generate more. If you make it thinner, you'll generate less. But this subcrustal creep layer here conductively heats the upper mantle rather than radiating heat to space due to the low thermal conductivity of anorthosite compared to the thermal conductivity of mantle rocks. So we're arguing that this prolongs lunar magmatism by essentially heating the mantle from the top down. So just to wrap up with some inclusions and interpretations. So multiple lines of evidence, including our multiple saturation point experiments, point to a shallow mantle source for the Chang'e 5 magmas. The compositions of those magmas and the Apollo high titanium basalts provide little to no evidence for there being creep in the deep mantle. It looks as though late stage ilmenite-bearing cumulates and the creep layer are disconnected in the lunar mantle. They do not move together. And the most plausible model for generating prolonged magmatism on the moon involves a subcrustal creep layer that heats the mantle from the top down. And I think we see evidence for this excavated by the Imbrium impact, but there must be a substantial portion of it there left under the crust for substantial periods of time to generate these melts so late in lunar history. And with that, I thank you for your attention, and I'm happy to tackle any questions you have.
Thank you so much, Steve. And then I guess we'll go ahead, we'll open the floor up to questions. Let me just look. Yeah, Claude, go ahead.
Steve, wonderful talk, but I did miss a bit of it, so I apologize for that. So you probably already covered this, but you've got a creep layer melting the mantle beneath it. Why doesn't that melt then assimilate the creep as it comes to the surface?
Very good question, and it's one I don't have a great answer to, but I'll speculate for you a little bit. So if we think back to some of Jeff Andrews Hanna's work and some of the Grail team's work, they pointed out gradients in the gravitational field of the moon, which to them were very suggestive of long-lived magma conduits, basically pipes from the mantle where we had fluxes of magma coming through over time. so the only way for my model to be correct is if the Chang'e 5 magma avoids this creep layer as it makes it through to the surface. How it actually did that, I don't know, but I will say that one of those gradients in gravity corresponding, again, if you believe their model, to long-lived magma conduits sits right under the Chang'e 5 landing site. And so I would suggest that perhaps this is a long-lived magma conduit, maybe to the Mons Rumker region that's well established, is well established by 2 billion years old and simply avoids this creep layer.
Right, right. 'Cause there's no way it could be pressure released through a 2.1 billion year impact or anything like that, because it's all been covered up, right? So
yeah, there's a nice thick basalt layer at that surface by that time, so it's yeah.
Because the only other way I could envisage is that there is the removal of the anorthosite crust or whatever crust was there to promote pressure release. But does your thermal modeling, you showed the 2 billion year no creep layer. It doesn't seem to indicate that that would be possible, does it?
Well, again, making the caveat that the absolute temperatures aren't that meaningful in that model, it would certainly be a lot harder.
Yeah. Okay.
And if we go back to some of Matthew's convective models, where he puts creep on the surface, or you can almost remove it from the system and have the same effect. The upper mantle is pretty cold at that point. It's elastic lithosphere. He needs, in his global models, the creep right below the crust in order to heat the upper mantle, and sort of locally we unsurprisingly are seeing the same thing.
Yeah, it's also interesting that the high thorium ejector seems to be correlated with plagioclase when you get on QuickMap and start playing, suggesting that the creep layer was potentially lower crustal.
Yes, and there's a nice paper from Paul Warren from 80s or 90s. I can't remember the year. Sorry, Paul, if you're on here. But he shows really this nice correlation, inverse correlation between thorium content of small craters and crater diameter, suggesting that the small craters, at least the bigger you make them, the less thorium that there is.
Exactly.
So the small craters are just reworking Imbrium ejecta, and the bigger ones that punch through deeper aren't seeing that creep layer. So whatever Imbrium excavated, it was deeper than what small craters, so to speak, are sampling.
Yeah. Thanks, Steve.
Yeah, thanks, Clive.
Any other questions? Chip, go ahead.
Hi, Steve. Great talk. Thank you. Yeah, just a quick question on Matthew's calculations. As you pointed out, there are small Mari deposits that people have suggested are 100 million years old. Some of these pyroclastic, some of these beads found in Chang'e 5 are thought to be volcanic and about a little over 100 million years old. What does his modeling say about the availability of heat for melting, at 100 million years ago?
Yeah, great question. So in his models, the amount of melt and the duration of there being essentially a partial melt zone in the mantle through time and through to the present day was not only dependent on where he put creep in the crustal column, but also dependent on his starting mantle temperature profile. And he, I wish I had that handy now, but I don't. He had basically three cases, a nominal case, a cold start, and a hot start. And in the hot start case, where the mantle is relatively hot, basically at the beginning of his models, he can make partial melt zones through to the present day. I'm not sure that that's necessarily supported by the seismic data that we have, as low resolution as it might be. But in order to quantify that, you probably need to know something about the present day lunoselenotherm. And I know there are groups, especially Anania Malik's group out in Arizona, that's working on trying to constrain the selenotherm. But unless you've got a better idea for, say, the temperature profile of the mantle at the start and the location of creep, it's difficult to quantify. But if those beads really are 120 million years old, I'll say I'm a little skeptical. If the irregular Mare patches are young, I kind of feel a little bit better about those. We need a heat source. And to me, I don't really see evidence for creep in the mantle. Lower crustal creep, that might do it.
Okay. Any other questions? Oh, we have one. Chingzu.
Can you hear me?
Yep, we got you.
Steve, a very nice talk. Could you clarify the involvement of creep or not in Chang'e 5? Because you said in one hand, it's neodymium isotope on the depleted side. And then on the other hand, you also show the mixing in the rubidium strontium ratio as well as samarium neodymium ratio, which is a nice mixing between the mantle and creep. So I would have thought that the neodymium itself is a mixed result between the two. And so it is still involves component of creep in Chang'e 5 sample rather than not having it at all, no?
Yeah, I showed the two-component mixing diagram, but I think two-component mixing is probably an oversimplification. So one way that you can vary those ratios in the source region is simply by trapping some bits of magma ocean liquid as you're crystallizing the cumulates. Now, ultimately, though, that liquid is evolving towards creep, and so we'll probably lie on something resembling a mixing line between the two. But I think, to simply mix creep sensu strictu with every mantle melt to define that mixing array is probably not correct. But if you do the calculation, if you take that sort of n-member composition and mix in a little bit of creep to get at the SMND ratio of the Chang'e 5 source, you really only need like about 1% creep in order to do it. So if there was some there, it's small and inconsequential.
Okay. Thank you.
Any more questions? Oh, Chip, you have another one?
I've got another question. Steve, I have to go and teach a class at 2 today. And I know one question I got this morning from the Brown group and the Brown early morning seminar, and I'll get in my class, is what is the mineralogy of creep? We know what its trace element chemistry is. Well, what's the mineralogy?
I don't know. That totally depends on what paper you look at and how you think about creep as a rock. You look at the creep basalts from the moon, like 15386. They're not even that iron rich. They look like a typical Mare basalt. So if you think this is the end product of extensor fractional crystallization, it should have a super low Mg number, but the creep basalts don't. So, in absence of a hand sample, then we're left with, all right, well, what do the models say? Magma ocean models, again, predict it would be very iron rich. There was a really nice paper that came out maybe a month or so ago showing that the creep liquid itself may actually undergo silicate liquid immiscibility. I know this was suggested by Clive and Larry and others a while ago, and now we have experiments to sort of push us further down that road. So maybe you have two components. Maybe you have the potassium rare earth element rich fraction, and you have a more granitic fraction. So I mean. Yeah, and then I'll take this even more complicated. Then you factor in mantle overturn, where you have work by essentially folks at Brown, Charlotte Wabuker, who showed that mantle convection can potentially start before the end of magma ocean crystallization. Now you're taking a bunch of really mafic high Mg numbers from the deep mantle, those minerals, and you're dumping them back into the magma ocean. That's going to change the Mg number, and it's going to change the mineralogy. So mineralogy of creep, I don't know. What do you think?
Well, that's what I was going to tell the class. I don't know. And that's what I told the Brown group today. I don't know.
Yeah, same here. I don't know what it is.
Thanks, Steve.
Thank you, Chip.
Well, Steve, I'll ask one question. So I know for the rare earth element pattern, there was a very sharp negative europium anomaly, and it looked to match up with the creep, and it looked to be more than what you see with other basalts that are non-creep. So what could be causing that sharp negative europium anomaly?
Plagioclase retention in the source region is a great way to do that. Doesn't have to be much. If you have plage retained in the source, it's going to hold on to all that europium 2+ during melting. And if you don't melt out the plage, that could enhance the depth essentially of the negative europium anomaly. It may have already been present, right? The source region may have crystallized from the magma ocean, after the crust started forming. But if not all of that plage was floated to the crust and some of it was retained in the source, and then again retained during melting, it'll hold on to that 2+ and deepen that anomaly.
Okay. Thank you so much. Any final thoughts, questions from anybody else in the audience?
I'll say props to the folks online that figured out the connection and how I named my piston cylinders. Looks like that was Dave Draper and Dan Dunlop. Good job.
Well, then I think that'll pretty much wrap it up for today. So once again, Steve, thank you so much. I'll give you a nice another round of applause.
Yeah, thank you for having me. Appreciate it.
Yeah. And then we'll do one quick final announcement before everybody goes. Next week, we will have Danielle Adams from the Flagstaff Dark Skies Coalition talking about the moon and Arabian skies, stages, stations, and standstills. Oh my. So hopefully we get to see you guys again next week. Thank you so much for coming. Please, everyone, enjoy your week. Again, thank you so much, Steve. Have a good one, everybody.